What you're about to see is a top-level illustrative view of modeling and simulation to support this tabletop exercise. At its core, digital mission engineering, or DME, is about understanding how missions operate in pan-domain environments across land, sea, air, space, and cyber realms, and how decisions, dependencies, and disruptions propagate through a system. While these methods can support detailed technical analysis, today the focus is on effects, availability, and consequences rather than performance metrics. The tool being used is Systems Toolkit, or SDK, which is widely applied across defense and industry to model space and pan-domain systems, including satellites, ground stations, vehicles, coverage, and their interactions with users on Earth. For this exercise, SDK is used primarily as a visualization tool and sense-making tool, rather than its intended use as an engineering analytical engine. The models you'll see are intentionally simplified and are not representative of any specific system. Their purpose is to help build a shared mental model of how space systems operate, how they can be disrupted, and why those disruptions matter. What you're seeing here is the operating environment for Phase 2, Initial Operations, represented digitally. Canada is supporting operations in Goodland, a northern country with very limited physical infrastructure, and neighbors Darkland, an aggressor. In this environment, space systems are foundational. The same space systems that enable military command and control, intelligence collection, and force protection are also critical to everyday life in Goodland, including civilian communications, healthcare, education, and banking systems. The key takeaway is that commercial space is a shared dependency. Let's start with how those space-enabled connections are established. This view illustrates traditional geosynchronous satellite communications. Satellites positioned over Canada and Goodland provide persistent, wide-area connectivity between national headquarters, deployed forces, and users on the ground. From an operational perspective, GeoSatcom is attractive because it is stable, predictable, and supports long-range connectivity across the globe in near real time. However, that same concentration creates risk. When a single satellite supports a large geographic area, disruption affects everyone within the footprint, military and civilian alike. The key takeaway here is that GEO provides persistence and scale, but concentrates risk. So what does GEO disruption look like in practice? Here, a ground-based jammer is introduced to interfere with the GEO satellite. Rather than attacking the satellite itself, the jammer transmits noise at the same frequency used for satellite communications. The satellite remains intact, but the signal becomes unstable. Because geosatellites cover such large areas, even relatively simple jamming can degrade communications across a wide region. This type of interference is often easy to implement and relatively low cost, which makes it an attractive option for non-state actors. The key takeaway here is that jamming is easy to implement, cheap, and geographically impactful. This drives interest in more resilient alternatives. Low Earth orbit systems operate very differently. Instead of a small number of fixed satellites, LEO constellations rely on many satellites moving rapidly overhead. In this scenario, I populated a simple LEO constellation totaling 36 satellites with attached comms and imaging sensors. Compared to Telesat's Lightspeed or SpaceX Starlink LEO constellations, this is quite a small number, but adequate enough to demonstrate LEO's capabilities. I have a coverage figure of merit overlay evaluating the revisit time. You can see that even with a fixed sensor, the average revisit time is very frequent and can be near continuous with enough satellites. Coverage on the ground is much smaller and is constantly changing. From a resilience perspective, this matters. Jamming becomes harder as users can transition between satellites as they move. The key takeaway here is that LEO enables resilience through numbers and motion. But resiliency isn't immunity. Disrupting LEO systems is more challenging, but still possible. Jammers can be more precise and persistent. With multiple jamming locations, this can easily be achieved. For Earth observation, a different technique is used: laser dazzling. A laser dazzler does not destroy the satellite. Instead, it temporarily overwhelms the sensor, much like shining a bright light into a camera lens. The satellite continues to operate, but the collected imagery is unusable for that pass. The key takeaway here is that counter space can be scaled up to counteract dynamic LEO constellations. This final view ties the picture together. Military operations, including command and control of mobile units in northern Goodland as they locate and target disruptor facilities, or defend areas of interest, the use of remotely piloted aircraft for reconnaissance and strike operations, and the streaming of evidence of war crimes to inform authorities and the public, are all critically dependent on these space services. At the same time, civilian services rely on the same systems. When communications or imagery are degraded, hospitals lose connectivity, education is disrupted, and financial services become unreliable. The key takeaway here is that military operational success and civilian harm are tightly linked. In this phase, TF-able forces enjoy increasing success against disruptor forces in northern Goodland. Various disruptor operations or jamming locations are taken out via remotely piloted aircraft strikes, coordinated with Earth observation data and orchestrated through satellite links. Several internment camps are identified with the same help of the aircraft and connected SATCOM and EO systems. Task forces are organized for rescue operations. Potential war crimes regarding maltreatment of detainees are disclosed to the public and authorities to discredit hostile actions. The key takeaway here is that operational success relies on coordination and persistence of multiple pan-domain assets. That success caused Darkland to escalate. In response to, and as a potential prelude to an invasion of northern Goodland, a major coordinated cyber attack is launched by Darkland against critical SATCOM and Earth observation services. It is key to note here that satellites don't operate in isolation. They depend on ground networks, softwares, and supply chains. Attacks on those systems can be just as damaging as attacks on the satellite itself. The key takeaway here is that the cyber domain is another vertical in modern warfare that critically enables pan-domain coordination. The impact is first felt in space. Cyber attacks can have huge impacts on space assets without any physical means of interference. False space situational awareness or navigation data can be fed to satellites, causing instrument mispointing, unnecessary maneuvers, and lead to disasters felt both in space and on the ground. Nothing is destroyed, but services are disrupted because the satellites are not able to function within its operational context. This can cause severe service outages that affect clients from across the globe, and in extreme cases, lead to catastrophic collisions with other objects in LEO. The key takeaway is that data integrity can be a weapon. The effects quickly propagate back to operations on the ground. On the ground, military operations are equally compromised. Command and control of mobile units in northern Goodland are limited to backup systems, which are easily jammed. Remotely piloted aircraft systems are grounded. Reliable data cannot be sent for reconnaissance, communications, or strike operations. Planned liberations and streaming of war crimes are halted as reliable links cannot be established. The key takeaway here is that cyber attacks critically compromise integrated digital systems. But military operations are not the only system affected. The loss of connectivity has widespread and indiscriminate implications. The effects disrupt Goodland's critical information infrastructure. Medical procedures are cancelled due to outages or lack of reliable navigation. Digital payment system outages cause financial instability when funds can't be sent to denied zones. Online education services are halted. Outages in GPS navigation for naval or ground transport pose risks for catastrophic accidents. The key takeaway is that cyberspace attacks are indiscriminate and increase humanitarian risk. At this point, the challenge is no longer technical. With limited clean terminals and degraded capacity, decisions must be made about who receives access and in what order. These decisions carry strategic, legal, and ethical weight, particularly when military objectives, civilian resilience, and obligations to protect vulnerable populations compete for the same scarce resources. This is where operational realities become policy decisions. The key takeaway here is that scarcity turns technical problems into hard decisions.